Okay, so I'm going to teach you a new concept called inertia. So inertia is the amount of resistance that an individual object has. The symbol for inertia is just a large I. Now, more importantly, the equation for inertia is mass times radius squared, where the radius is only squared. And that simplified is mr squared. Now, the units of mass are kilograms and the units of radius are meters. So, kilograms times meter squared would be the units for inertia. And you can say that inertia is similar to mass. Okay, it's very important that you remember that the net force is equal to mass times acceleration. It is also important that you remember that when you're dealing with rotations, you don't use tangential acceleration, which is expressed in A, but you would use angular acceleration, which is the little fishy thing. And how torque is considered a rotational force, like that's important to know too. Well, since F is equal to ma, you would think that torque is equal to mass times angular acceleration, right? Okay, wrong. You were so close, yet so far. Very, very close. So now think back to inertia and how it relates to mass and distance because it's equal to mr squared. So since it relates to mass, you replace torque equals m times angular acceleration with torque is equal to inertia times angular acceleration, just like F is equal to ma. And to sum it up, net torque is inertia times angular acceleration, which is also equal to the net force multiplied by the radius multiplied by sine theta, which you already knew. Okay, so let's answer this problem. Three massless rods are free to rotate about an axis at their left end. The same force is applied to the right end of each rod. Objects with different masses are attached to the rods, but the total mass of the objects is the same for each rod. Rank the angular acceleration of the rods largest to smallest. Alright, so first things first, we know that inertia is equal to mr squared. We also know that the net of anything is just everything added together. So the net inertia is just m1r1 squared plus m2r2 squared plus m3r3 squared and so on. So let's draw A. So there's a little line. That red point is the axis perpendicular to the page, or the axis of rotation. That little silver spot is this M. That silver spot is another M, and this spot is the third M. To make this easier, let's give a random value to M. Let's just say that M is equal to, I don't know, how about 4? Yeah, 4. And that R is equal to 5. So R is your entire pole. Here I'm making it prettier for you. And we know that m1r1 squared plus m2r2 squared plus m3r3 squared is the net torque. Net inertia. So since we know that, just substitute those values with the values we had given before. So m1 would be 4, r1 would be 5 over 3, because since r is equal to 5, that means that this distance is 5 divided by 3. And m2 is still 4, and the middle one is 5 divided by 2 squared, and m3 is still 4, and r3 is equal to 5 because it's the full rod. And now you just solve for that. Okay, I'm sorry, I made a mistake. R1 is not equal to 5 over 3. R1 is equal to 0 because since it's right here, it's right on the axis of rotation. So you just assume that it's 0. I'm sorry. So the correct equation is m1 times r1 plus m2 times r2 squared plus m3 plus r3 squared. Sorry for the confusion. So now just solve. You get that, and then your final answer is 125 kilograms times meter squared for rod A. Okay, now let's do B. So that's the rod for B. Those are the two M points. That's the axis of rotation, but the middle one is 2M, while the one all the way to the end is just M. M is still equal to 4, and R is still equal to 5. Remember that R is the length of the entire rod. Okay, so we know that the equation for net inertia is equal to m1 r1 squared plus m2 r2 squared. So just plug in the values that we know. We know that m1 is 2m, and since m is 4, that means that m1 is 2 multiplied by 4. We know that r1 is going to be 5 divided by 2, because since 5 is just r, and M1 is located in the center of the rod right here. And we know that M2 is just 4, and R2 is just 5. So you just solve and you get that the answer is 150 kilograms times meters squared. Okay, so let's do the next one. There's a line. Here's your first M. Here's your second M. There's your axis of rotation. There's your R, which represents the entire rod. Hold up, let me fix this. There's your 3M. Oh, excuse me, there is no M in the middle of the rod. For C, the rod is just one dot of 3M all the way to the other side of the axis of rotation. Okay, since there's only one point here, the net inertia is just M1 R1 squared. And M is still 4 and R is still 5. So this becomes 4 times 3, because since it's 3m, and r1 becomes 5 squared, and you end up getting that your net inertia is 300 kilograms times meter squared. Okay, so we know that the inertia for rod A is 125, for B it's 150, and for C it's 300 kilograms times meter squared. Since the force applied was the same in all three rods, and torque is equal to inertia times angular acceleration, and I'd asked you to rank the angular acceleration largest to smallest, well, you just know that it's A, B, then C, because since inertia is the smallest in A, the angular acceleration has to be the largest. And then for B, it's the middle one, so it would be the middle one. And since inertia is 300 for C, that means angular acceleration has to be slow. Okay, so now let's do this problem. At a given instant, an object has an angular velocity. It also has an angular acceleration due to the torques that are present. Therefore, the angular velocity is changing. Does the angular velocity at this instant increase, decrease, or remain the same if additional torques are applied so as to make the net torque suddenly equal to 0? Okay, so A says that there's going to be an additional torque, which is another way to say an additional force being applied, so that the net torque is equal to 0. So, if there are more forces being applied, that means it's going to be harder to move. So that means that the velocity is going to go slower, because the more force there is, the slower it's going to go. And now B asks you that what happens to the angular velocity if all torques are suddenly removed? Okay, since there are no torques, that means that there's nothing being applied to the angular velocity. So there's nothing being taken away or nothing being added to it. So that means it'll just remain the same. Okay, now number 13. The space probe in the drawing is initially moving with a constant translational velocity and zero angular velocity. When the two engines are fired, each generating thrust of magnitude t, does the translational velocity increase, decrease, or remain the same? Okay, well, if both thrusts are turned on, it actually gets faster because since they're on opposite sides, they're on since they're on opposite sides and going on opposite directions, that means that it will start moving. But that's for the... Okay, I am so sorry. I am brain dead. Okay, let me start over. The translational velocity, that means the regular velocity. It'll remain the same in this case for A because nothing is being applied that'll make it go faster or slower to the left, right, up, or down. But for part B, it asks about angular velocity. Since the thrusts are on opposite sides and going in opposite directions, it will go faster. The reason this happens is because pretend you have your hands on a steering wheel, each hand on each side, and let's say your left hand goes down and your right hand goes up. There will be a movement in the steering wheel. So that means that your angular velocity will go faster. Alright, so a clay vase on a potter's wheel experiences an angular acceleration of 8 radians per second squared due to the application of a 10 Newton meter torque. Find the total moment of inertia of the vase and the wheel. Okay, so the first thing you want to do is write down your values. You know that the torque is 10 Newton meters and the acceleration is 8 radians per second squared. You know that torque is inertia angular acceleration, and they're asking for the inertia, so just plug into the equation, and 10 divided by 8 is 1.25 kilograms times meters squared. Okay, so a solid circular disc has a mass of 1.2 kilograms and a radius of 0.16 meters. Each of the three identical thin rods has a mass of 0.15 kilograms. The rods are attached perpendicularly to the plane of the disc at its outer edge to form a three-legged stool. Find the moment of inertia of the stool with respect to an axis that is perpendicular to the plane of the disc at its center. Okay, well, we know that inertia here is mr squared for each of the rods. So we know that the m for each rod is 0.15 and the r is 0.16 squared. So you solve that and you get 0.00384. Since there are 3 rods, you multiply that number by 3 or you just add it to itself 3 by 3 times. And once you do that, you get 0.01152. Okay, now to find the inertia for the disc, we have to use the equation sheet that Burgos gives us. So we know that it's a solid circular disc because that's what the problem tells us. The inertia for a solid cylinder or a disc is half of mr squared, which in this case is half of 1.2 kilograms times 0.16 squared. You do that and you solve and you get 0.01536. Now, since it asks you for the total inertia of the stool and the rods, you just add those two values together and your final answer is 0.0269 kilograms times meters squared. So a ceiling fan is turned on and a net torque of 1.8 Newton meters is applied to the blades. The blades have a total moment of inertia of 0.22 kilograms times meters squared. What is the angular acceleration of the blades? Okay, we know that torque is inertia times acceleration, and that torque they gave us is 1.8 newtons meters, and the inertia they gave us is 0.22 kilograms times meter squared. So torque is inertia acceleration. Just plug in, divide 1.8 by 0.22 to get the acceleration, and you get 8.18 radians per second squared. Okay, so a 9.75 meter ladder with a mass of 23.2 kilograms lies flat on the ground. A painter grabs the top end of the ladder and pulls straight upward with a force of 245 newtons. At the instant the top of the ladder leaves the ground, the ladder experiences an angular acceleration of 1.8 radians per second squared. The ladder's center of gravity lies halfway between the top and the bottom ends. What is the net torque acting on the ladder, and what is the ladder's moment of inertia? Okay, so first let's write down your values. Mass equals 23.2, force equals 245 newtons, your angular acceleration is 1.8 radians per second squared, and the distance is 9.75 meters. So let's draw this out. That's the ladder. Those are the halfway points of the ladder. There you go for the ladder. It's 245 newtons pointing upwards. You know that your net torque is force times distance. So you know that your net torque is 245 multiplied by 4.875. The reason it's not 9.75 is because it tells you that the center of gravity is halfway between the ladder, so half of 9.75. You solve that and you get that for your torque. So that's the answer to A. Now to get B, you know that inertia is equal to mr squared, and you know your m and you know your r. So you just plug in and you get that your answer is 226.2 kilograms times meter squared. And that's your final answer.